Tianmin is an assistant professor at the Department of Johns Hopkins University and the director of the Social Cognitive AI Lab. His research focuses on building human-centered AI systems with social intelligence and combining ideas from machine learning, computer vision, robotics, and cognitive science. Before joining JHU, he was a research scientist at MIT, working with Josh Tenenbaum and Antonio Torralba. Today, he will give a talk titled Scaling Model-Based Theory of Mind for Socially Intelligent Embodied Partners. Let's welcome Tim.
Right. Yeah, thanks for the introduction. I'm going to start with just to motivate why do we need embodied partners and why they need to be socially intelligent. So imagine you want to build robots that can help you around in your homes, in a hospital, or you want to have robot teammates that can work with you, or even maybe just other robots. They have to be able to understand you or other agents. Here's a cover from Eureka a couple of years ago. You can imagine a robot that can be very physically capable. You can build a wonderful paper pyramid. But if that's not really what you want the robot to do, it is actually not helping you at all. In fact, it could be even hurting you. So really, we have to have this basic fundamental kind of capacity for robot to understand humans. But what I mean by understanding human, so I will use this example to demonstrate the kind of human understanding we want robot to have. So look at this picture. Raise your hand if you think the person on the right-hand side is helping. All right, so I have showed this to over 1,000 people now. Only 2 people raised their hands. Both of them were sitting in the back in a very large room, could not see the picture. If you can see the picture, no one will actually raise their hand. We tested this with early version of the multimodal language model. Nowadays, they can be better, but I just want to use this example to demonstrate the kind of error you may make in answering this situation. So the model actually gives you very coherent explanation. Actually, the action was correct. Indeed, the person on the right-hand side is holding the chair, but the intent was the opposite. It's not really helping. I just want to use this kind of example to show you understanding human doesn't mean you just recognize actions. You actually want to recognize the cause of the actions. You want to reason why they are taking these actions. So this basically is what we call theory of mind reasoning capacity. So theory of mind is this fundamental capacity that people, even infants, can have, where we can look at people's behavior and try to reason about these hidden mental variables that can cause these kind of behaviors. So this could be goals and belief and other kind of mental variables for a person. So looking at this example again, you can recognize the goals and belief of the person on the left-hand side. You can recognize that the person on the right-hand side, left-hand side, has this false belief, right? So the belief in the person on the left-hand side was the chair was not moved, which was, of course, inconsistent with the actual physical state. And crucially, this false belief was caused by the person on the right-hand side. So you have to really understand the mental states and also the mental state between multiple agents to kind of appreciate this kind of social situation. So in recent years, people have been really interested in understanding whether or not language model have theory minds, and there are many papers in recent years trying to study this. However, if you look at the kind of benchmark they are using, it is very simple. You have a very short story about some people doing some things, interacting with 1 or 2 objects in a very simple environment. And then looking at this very simple text, you want to answer a question about a person's mental state. But this is really different from what you want a robot to do. You put a robot in a house, like this very cute actual robot from Amazon. The robot needs to watch your behavior, listen to what you're talking about, talking with each other, talking to robots, having these kind of multimodal streaming inputs, and really try to understand what you're trying to do and whether or not the robot can help you. So no one actually will write this very simple question for a robot. The robot needs to understand whether or not you need to reason about the mental state for a person, what kind of mental state you want to understand about this person, and how you can provide assistance. So we need to really go beyond this simple task-based kind of QA having more risk settings. In start, I want to start with what I call embodied multimodal DMIs. Where I need to form a coherent mental picture based on my multimodal inputs. It could be any kind of multimodal inputs, video, text, speech, whatever. And use this understanding about a person's mental picture to do planning. So you want to use DMI reasoning not as a downstream task, but as an intermediate representation about person, and use that to enhance your decision making. So I'll give you very, very simple examples. Suppose you want to build a robot that can help you around in your house. The robot can see what you're doing. So you see this action. You're not really sure the the task you really want to do. So you have some hypothesis, robot form hypothesis about the task you want to perform with varying degree of confidence, right? So you have this very uncertain goal inference. If the goal inference is really uncertain, you shouldn't do anything irrational. You shouldn't just running guess on the thing you want to do and help with that incorrect goal. Instead, maybe you want to observe more actions. So with more action observation, you can update your inference and become more confident in your goal inference. When it's very confident, then you can start to help with specific tasks. So this is just a very simple example to demonstrate the DMI reasoning you need a robot to do in embodied settings and how that influences your decision-making process. All right, so the first thing we have done here is that before we actually put robot to a house to interact with people, we want to first evaluate their behavior, their ability to understand people's mental states. So we put this benchmark called multimodal DMI question answering. So the idea is that you show a video of people's behavior in your house and some task description about the environment and the action. You can show either video or text or both to a model and ask model to understand a person's mental states and answer the questions. Crucially, the answers are usually uncertain. So you really need to have this graded judgment about uncertainty and choose the one that you feel like is more likely to be true. So we have this home simulation we built several years ago when I was still at MIT. It's called Virtual Home Social, where we can create different apartments, put people in these simulate people in this apartment to generate a lot of videos. With this video, we can generate questions about person's mental states, including a belief and goal. Here's a very simple belief inference example. I'm not showing the whole video or the text, just showing the key frames and the key description. So you have a person called Jennifer. So Jennifer is walking towards cabinets in the living room. In the cabinet, there's a bag of chips among other objects, but there are no cupcakes in the cabinets. However, you may find some cupcakes inside the microwave, which is right now in the kitchen. So that's the Guangzhou state. The action again is Jennifer is walking towards the cabinet, which is inside of the living room. So the question is, if Jennifer has been trying to get a cupcake, which one of the following statement is more likely to be true? A, Jennifer thinks there isn't a cupcake inside the cabinet. B, Jennifer thinks there is a cupcake inside the cabinet. I've already showed the Guangzhou's the correct answer here. Of course, you can imagine different hypotheses about Jennifer's mental states, but these are the two options I provide to you. And the more likely one is B, because why else would Jennifer go to the cabinet where you cannot find, where Jennifer thinks that there's no where else you would and go to the why else you would go to cabinets if Jennifer thinks there isn't cupcakes inside cabinets. So that's the more reasonable explanation about Jennifer's behavior. Again, you're not really sure, 100% sure about Jennifer's belief, but that's the more likely explanation. Any question about this? All right. We can also extend this to multi-agent situations. We need to think about how one agent thinks about other agents' mental states. Here's an example of social goal inference problem. You have two agents now, Kevin and Jessica. Kevin is trying to find, he's looking for a magazine, and he asks Jessica, where is the magazine? Have you seen the magazine? Jessica said, yeah, it's in the cabinet in the bedroom. All right, so Kevin believes that, goes to the cabinet, but finds nothing. All right, so the question is, if Jessica actually knows what's inside the cabinet in the bedroom, which of the following is more likely to be true? A, Jessica is trying to help Kevin. B, she's actually trying to hinder Kevin. Raise your hand if you think it's A. Raise your hand, one. Okay, raise your hand if you think it's B. A lot more B. I'd like to actually understand why you think A. Actually, can you say why do you think it's helping?
She knows the position of the item that it's required, so she's just helping him.
Right. I do need to clarify a little bit, right? So what happened is Kevin actually goes there and finds nothing inside the cabinet. So that's right. So that's yeah. Okay. Like most of you would choose B is more likely to be true. All right, so I have to give you this example. People can do this. We actually show very high accuracy from human participants in the benchmarks. But why? And whether or not we can build models that can also do this kind of reasoning. So from Conley's study, people argue that, and also have evidence to show that, we can reason about other people's mental states because we have this generative model of the physical world and people acting in the physical world that can allow us to reason about how agents act with respect to the physical constraints. The kind of computational model can build to replicate this behavior or this generative model is to have a joint kind of world modeling and agent modeling. So agent acts based on their understanding about how the world works. So that's one model. But you also have agents' own mental states, such as belief and goal. And jointly, based on your understanding about the world and your own mental states, you can make plans to act, right? So that's kind of a general kind of concept behind generative modeling for the world and agents. But you use the kind of agent model in a recursive way to reason about other people's mental states. So think about a robot watching people's behavior, a person's behavior. How does these robots infer this person's mental state based on the behavior? Well, you have a kind of a lower level agent model for the robot to approximate this person's behavior, right? So the robot has this level 1 agent model. You can use this level 0, lower level agent model to approximate human behavior in order to really reason about the person's mental state. We call this method Bayesian inverse planning. The idea is that you want to watch a person's action taking at certain physical states and use this evidence to infer the mental state of person's goal, such as the person's goal and belief. This inference method can be decomposed into two parts, the two main parts. You have the prior about belief and goals, but more crucially, you have this likelihood term, which is try to imagine what kind of actions a person will take, but would take if they will have this hypothetical goal and hypothetical belief. So you propose some kind of possible goal and belief based on your prior, and you want to simulate this person's action based on this low-level agent model, right? So this is a generative model, so you can use it to generate possible actions. You compare that with the observed action that gives you this likelihood term. So if your hypothesis really gives you actions that looks very close to the observed action from human, you get very high likelihood. So that's kind of basic idea behind inverse planning. Basically, you solve the problem of inference, minus the inference by doing this forward simulation, basically the planning part. And you invert this process, you can do minus the inference. Any questions about this? All right, so this is very simple but elegant model. The question is, how we can scale this out up to really understand real world people's behavior. So let's look at this example, the single agent belief inference example. You can kind of use the POMDP, so partially observable MDP, to approximate this agent behavior. And use that, you can have this likelihood term, which is, what is the likely action of Jennifer? Suppose Jennifer had this belief and this goal. So that's good, but when you have multi-agent situations, this is not sufficient. You need to have an interactive POMDP. So in this case, you have a two-level interactive POMDP where in order to estimate likelihoods for Jessica's action, not only you need to have Jessica's own belief and goal, but also infer this recursive belief, right? So how Jessica infer Kevin's belief and goal. So you can also go to even higher order reasoning. So you have this higher order intermediate DP. If you need to answer a question like, say, what does Alex think, Sally thinks, Anne thinks the milk is? So you can do, it's endless. There are many, many different kinds of agent model people have proposed for different kinds of mental state inference. But crucially, people have to manually create these kind of models by themselves. This is not really scalable. How do you even know what kind of model you need to actually define for these agents in order to answer the question about, in order to infer these agents' mental states in different situations. So one of the reasons what we have done is to automate the whole process. So there's no human involved. No one need to define agent model for any situation. You can automatically discover minimal agent model to understand person's behavior. So given any situation, any observation of a person's behavior or several people's behavior, and then a question you want to answer about one of the person's mental states, you can first extract observable variables. So here you have a sequence of states and also sequence of actions of the person taken at the states. You can then try to propose some kind of minimally necessary mental variables on top of the observable variables. So for example, you can propose mental variables such as observation, so that's the O here, and also the belief of the person, that's the B variable. That gives you kind of initial idea about what kind of agent model you would need to understand this person's behavior. Using this, you can then do the whole inverse planning business that I just show you based on this particular agent model. And specifically, the agent model here will be a Bayesian network. You get the inference. The inference right now is not very certain. You have 60% chance for one, 50% chance for the other. So you want to kind of model the utility of the inference result here, which is you want to maximize the certainty. You want to get a very certain answer, but also you want to minimize the model complexity. You don't want to, have an overly complicated model to describe this agent behavior. So let's say in this case, the certainty is not really very high. Maybe you're missing some key latent variables here. So for example, you can imagine people's behavior were not only governed by their observation and belief, but also their goals. So you can introduce additional goal variable here and try it again and see whether or not it helps. So you can do these iterative refinements until you are very happy about your answer, then you can produce the final answer. Each of these steps can be done by a language model, so it is quite open-ended. Crucially, for Bayesian inverse planning part, given a specific model, this can also be done in an automated way. So conventionally, given a base net for agent model, there are many, many manual design choices you have to make. What are the kind of representations you can define for observation, belief, and goal, and state and actions? Well, it's very hard to define a kind of unified one. How do you define the hypothesis space for each of these latent variables? Right? What is the hypothesis space for goal and belief? Well, actually, they are infinite. So it is, again, very hard to manually define some useful ones. So here we want to automate the process to make it more open-ended. So the first thing we can do here is that we can represent each one of these variables using natural language, which is very generic. So you can describe anything, well, most of the thing in natural language. For hypothesis sampling, you don't need to define hypothesis space, but you can just ask the language model to propose top hypothesis based on the context. So this will be basic sampling from an infinite hypothesis space, essentially. There's also this inference part. So remember, each of these model is a base net. So for base net, you want to define local conditionals, which again was traditionally done manually. So here we can also again use the language model to estimate how likely kind of likelihood, the local conditionals terms, right? For example, if you have a states condition, how likely you're going to have this observation for the agents. This again can be done by language model automatically. So this basically constructs an inference problem using these base nets you proposed earlier without having any manual specification for the model. Once you have this model constructed, then you can use your favorite sampling-based inference algorithm, improvement sampling, MCMC, sequential Monte Carlo, to actually compute the final posterior distribution and get the answer. So the final answer is still done by explicit kind of Bayesian inference, but the model construction was done by a language model. All right, any questions so far? Okay. Our security side, if you have multimodal fusion, again, we represent everything in language, so it's quite easy to kind of use VRM to fuse everything together to get the test inputs for the whole model. All right, so this is an example of how AutoTOM works. This is a story about agents, and there's a question about agents' mental states. You first extract a sequence of the states and action as the observable variables. You propose initial model that has observation and belief. You get the answer, which is the inference is half and half. So it's not really a certain inference. It has very low utility for the model. You want to adjust this model by introduce additional terms. So here you have additional variable G, basically the goal of the agent, that also introduce additional additional terms in your Bayesian inference. Then based on this new model, you can get a lot more confidence answer. We tested on many different memories in benchmarks. For these different benchmarks, you need to actually discover different kind of model to accurately answer the question. So we use GP4 as the backend model for AutoTOM, and outperformed across different benchmarks, outperform all of the language model and reasoning models. But if you look at actually different kind of mental reasoning questions, the result becomes a little bit more even more interesting. So for example, if you look at from left, you have simple question like say you don't need to do any state reasoning at all. You just need to predict next states given the action of the agent, all the way to go inference at a higher level. Right, so let's look at a very typical one. If you want to build a robot that can help you, one of the common inference question is how you can infer a person's goal, right? So that's a single agent goal inference. If you look at these kind of tasks, reasoning models are really very bad. These are not even the most recent one. We tested more recent one, like say Gemini 3. They are still very much struggling at the goal inference questions. But with AutoTOM, we use a lot smaller kind of language model as backend, but do explicit Bayesian inference and agent model proposal. You can achieve more than double the accuracy, almost double the accuracy. And it actually doesn't require more compute to compared to reasoning models. All right, so that's reasoning, but we want to also use the reasoning to support decision making, particularly human-robot collaboration. I will use one very simple example here. So we have this home simulation built earlier. Use the simulation can set up this challenge called watch and help. So we have two agents in the environment. You have a main agent that tries to perform a kind of a household task. So this could be a different kind of household task, and it takes the main agent very long time to finish one task. So you want to have a help agent to come in and help main agent. Crucially, help agent does not know the Guangzhou's goal, so you need to watch main agent actions, infer main agent's goal, and to help reach the inferred goal faster. Main agent is controlled by human, help agent is controlled by AI. Then we can evaluate what kind of speed up we can provide by helping the main agent compared to just having main agents doing the task alone. All right, so here's the result. So the random, we can pair different kind of reasoning models with the same helping planner. And you can see that actually if you use GP4, it doesn't perform better than randomly guess a goal. And really you need some kind of a robust kind of Bayesian inference with multiple hypotheses, and also keep the different kind of confidence for the hypothesis to be able to help the agents. We tried reasoning models. None of them are actually fast enough for real-time deployments. In addition to physical actions, you can also introduce communication. Particularly, we're kind of interested in how you can enable agent to initiate communication whenever necessary. For example, you can ask for clarification questions when you are really uncertain. You can ask for additional information from human. You can also provide information that you think human needs. So these are basically the kind of proactive communication you can imagine for an agent to engage with humans when the agent is trying to help with human. So again, we kind of leverage the ability to infer each other's minds to optimize communication. So the ultimate situation you want two agents to achieve is that they actually share the same mind. They know exactly what each other is going to do. But that's not the case in real world. What they can do is you can try to infer each other's minds and detect this misalignment between the two minds and use communication as a way to minimize the kind of misalignment between the two minds. So we run again a user study in human in Washington Health tasks where we ask human to work with different kind of AI agents driven by different methods. So you can see that if you use purely language model driven agents, it doesn't really help much. Even though it can generate natural language communication with humans that human can understand, they are not oftentimes really helpful. Here we also run subjective kind of evaluation with human participants. So here I want to show two results. So people find language model driven agents, purely language model driven agents, taught the most. However, they also find the communication not very useful. So they are actually a lot of redundant kind of communication generated by the language model. That's annoying, but not really helping the real task. This is another kind of example we recently done. So I'm an amateur chef. I like to cook whenever I have time. And then during cooking, I also like to play very loud music in my house. So this really is not a really good combination if you want to instruct a robot to help me. The very basic capacity, speech recognition will fail a lot of time. It also doesn't help I have accent. So how do we actually enable robot to understand human intent when there's a very noisy speech? So really we're treating speech recognition not as just speech recognition, but actually a multimodal theorem by reasoning problem. So you have visual input, you have the surrounding environment, you will have observation of a surrounding environment, you have past observation of a person's action from your visual input. Then you also have speech. So generally you want to paint this mental picture of what the person has been trying to do and try to infer the goal and also the intended task human assigned to the robots. So then you can have more robust kind of inference about what the human actually want the robot to do. So we did this kind of human study. This is a mock apartment in our on campus. We asked people to cook anything they want, play their favorite music in the background. During this cooking task, they can ask robot to pick out different kind of ingredients to help the human. So if you use language model like say Gemini with the same kind of visual and audio input, it doesn't really help you most of the time. It fails most of the time actually. But with multimodal theory reasoning, you can double the success rate. All right, now what I'm doing, I have a little bit of time. All right, so we show that actually you can use theory reasoning to support decision-making tasks, particularly in a household situation that I demonstrated here. One of the kind of key limitation here is that we still need this kind of expensive explicit Bayesian inference, right? You call language model as a backend, but you need to call it multiple times to propose agent model to do hypothesis sampling to estimate the local conditionals. It doesn't seem to be very efficient. So, so the next question we are trying to ask here is that can you still use kind of inverse planning idea, but try to internalize the inverse planning process into a single language model so that you can still do end-to-end kind of inference, but a language model itself can kind of try to do this inverse planning process implicitly and internalize kind of the Bayesian inverse planning approach. So the basic idea is that we want to amortize Bayesian inverse planning. Just to remind you again, inverse planning problem here is that you have a sequence of state and actions of person. Then you want to infer the mental states, based on action likelihood, and you apply about the mental state hypothesis. So this is a basic setup for Bayesian inverse planning. One kind of idea you can do can apply here is that you can train language model to do variational inference, and to get language model to approximate the true post distribution here. And the way you traditionally train variational inference is to maximize the elbow objective. The problem here is that now you're dealing with distribution, a positive distribution in infinite hypothesis space. It is actually not that trivial to optimize this elbow objective. So the idea is that maybe you can kind of use the kind of a common IO training recipe for language model, but now use it for kind of internalizing inverse planning. So the idea is that you can ask the model to look at the behavior and propose multiple top hypotheses about the mental states and the corresponding probabilities, right? So you don't need to produce the whole distribution because it's infinite, but only the top hypothesis and the corresponding probabilities. So these are the and variables and also the corresponding and probabilities. So the problem is how we can evaluate these samples using reinforcement learning to train language model. Well, we're going to go back to this elbow objective. So let's say you have a bunch of n hypotheses and corresponding q. Yeah, you can actually just plug into elbow to get the rewards here. We call this self-supervised reward because you actually do not need any Guang-Chil's mental state during training at all. It is what you need to do is you still need to do inverse planning during training. So you need to estimate these hypotheses, the likelihood of the hypothesis, and the prior of the hypothesis. But again, this can be done by, in most cases, it can be done by a language model, a pre-trained language model. So during training, you can do this inverse planning process to check whether or not the hypothesis you propose, the current hypothesis proposed by your current model, can be behavioral consistent. Basically, can explain the observed behavior. But also, you want to encourage the diversity. So you also have this entropy for the proposals you produce. But again, combine these two, these are basically the elbow objective. So by maximizing rewards, you're actually optimizing the same elbow objective. All right, so we kind of introduced the idea about self-supervised RL. So you do not need any Guang-Chil's mental states. And this is actually a very appealing kind of property of the method because in real world, you can get a lot of human behavior, but it's very, very hard, almost impossible to get Guang-Chil's human and mental state annotations, right? How you can get actually what people are thinking. It is almost impossible in many cases. However, if you do self-supervised IO, you actually do not need any Guang-Chil's mental states. All you need to do is to ask model to propose hypothesis and use inverse planning to estimate how good this hypothesis really is. So again, the idea is that you kind of propose kind of IO training recipe to kind of internalize inverse planning inside the language model without any Guang-Chil's annotations. Any question about this? All right, so how does it work? We're going to go back to the household situation I showed you earlier. We have question and answer benchmarks. We have a proactive assistant benchmark. For all of these situations, you can use synthetic training data to train models. So these are the kind of single agent behavior kind of trajectories you can generate in the simulation. Again, there's no mental state annotation at all. You just have the sequence of actions. The likelihood and prior turn can also be estimated by a very small Bayesian language model. So the idea is I want to use this data to fine-tune the small language model so that they can kind of internalize the inverse planning process. Here's the result on question and answer. So the orange ones are the pre-trained language models, including small open source model and large closed source model. The blue bars, so they are the explicit model-based approach that need to repeatedly call language model backends multiple times. So that also includes autotom method I introduced before. So if you look at the computes, those models actually a lot more expensive than the single call for a base model, even though they can improve the accuracy a little bit upon the base model. However, if you could use Mind Zero to kind of train this more open source model, even though you don't introduce any additional compute because it is still single pass end-to-end kind of results, but then the accuracy will be a lot better, and now you can kind of compete that against the state-of method that use the large models as a backend, but then you repeatedly call the large models. So that's quite nice, but how does it work with assistance? So this is the result from for assistance. You apply again the same ideas. You train a very small model using Mind Zero, and again we introduce no additional cost, but the speed up performance is a lot better than the base model, and it actually can even outperform the much larger kind of closed source model. All right, so I want to do a very quick summary. So I've kind of introduced the idea about using model-based kind of approach to do multimodal theorem reasoning that can eventually enhance collaboration between human and robots. The kind of basic idea is that you want to automate the process of agent modeling for model-based inference. But then the inference doesn't need to be very expensive. You can kind of internalize the whole process into a single language model by using what we call self-supervised RL approach. And I think was how we doing though. Okay, right. I just have one thing, very quick thing. So this is nice, but then I would say there's a very fundamental limit here, which is a lot of the work I've shown here assume you can use natural language to represent everything, the physical state, the actions, the mental states. It is limiting in some sense, particularly when you want to infer 3D kind of spatial reasoning happening inside a person's mind. So we also want to have actually some kind of 3D modeling for the belief of a person that's represented not in natural language, but in kind of spatial representation about the environment. So we have this reason what's that try to model agent's belief using explicit 3D representation, where the agent will look at partial elevation of the environment used from RGB input to continually update the whole imagination for the whole 3D world. So this includes also the part that you cannot really see, but you can use your context to imagine the whole 3D space. And with this kind of 3D imagination, you can do planning. So this is a simple kind of a fun experiment we did with the robots. So the robot is driven by this 3D belief model. We did this hide and seek experiment with the robots where we hide the objects in the unusual location inside the environment that the robot has never been to. So the robot has no prior knowledge about the environment. You need to look for these objects. So this is an example. The robot driven by our model can very quickly find objects, but if you use the Gemini to drive the robots, you will oftentimes lead the robot to a dead end. So the kind of idea is that eventually we want to use a kind of 3D model to enhance the mental representation for the agents. So you don't just infer mental states in language space, but also in the 3D world space. All right, with that, I want to thank you again and welcome any questions.
Thanks, Gary. Yeah, here's the Q&A section, and if anyone has any questions. I have two questions, and the first one is I noticed that in some previous tables, the self-mind augmented LM framework is much out from the LM baseline, and I think with the recent progress of the reasoning LMs, do you think it will emerge the self-mind ability from its training or post-training? Will it cover this gap naturally from its training itself?
Right. I think so. Several things. I think right now, even with the more recent models, it still struggle with some of the mental reasoning question, like say Go inference. But I think that with the more recent approach, like say Mind Zero, we are trying to actually try to answer that question. How can we kind of train language model to reason to enhance its reasoning capacity, mental reasoning capacity? I think my hypothesis is that the reason why we haven't observed reasoning models, the kind of a strong mental reasoning capacity for reasoning model, is that the way we train models, they are not really trained to try to understand people's mental states. So I think the kind of hypothesis I have is we want to train this model using multi-agent interaction experiences. You really want to train this model to perform multi-agent tasks, multi-agent planning tasks. Maybe the strong kind of mental reasoning capacity can emerge through those kind of training. I think the manual is really one of the kind of early step we're taking towards that direction.
Yes, thank you. Yeah, thank you. And I have another question is, I think you introduced the many potential application of the scalable social self-minded social intelligence and like including chatbots and human-robot collaboration. And what do you think is the direction that is most worthwhile exploring in the current time?
All right, so there's this actually very interesting paper from Di Yan's group at Stanford. So it's called Cooper Bench. So it's a benchmark for multi-agent collaboration on coding tasks. What they found is that when you have multiple agents trying to perform coding tasks together, they perform worse, consistent worse than a single agent trying to solve the same task. And what they found is that, for example, they can communicate with each other, but the communication is not really grounded and but a lot of time repetitive and not really valuable or informative. It helps agent to figure out whether or not you need to repeat the same task because it can inform other agents what you are doing, but you cannot go much beyond that. So I think again, this is my hypothesis. You have to have some kind of a grounded understanding about each other's mind, condition that collaborate task context, so that I can more effectively communicate with each other, right? So even if you're not interested in human AI collaboration, you want to build multiple AI to work on tasks that single agent cannot easily do. You still, this is my hypothesis. You still need to endow some kind of mental reasoning capacity for these agents.
Yeah, so you think it will raise the upfront of multi-agent like AI system?
Right. And then again, I think without very good mental capacity, I kind of doubt the agent can really effectively collaborate with each other.
Thank you very much. And questions from audience?
Thanks for the great talk. I have a question that do you think the mental world modeling of AI agents is similar to the mental world modeling of humans, given that AI agents actually only have the condition of context and tools maybe, but for human it's much more black box?
Yeah, it doesn't have to be human-like, to be honest. I think, okay, so if your goal is to understand people's mental world model, then you need to make sure you understand how people update their mental world model. But if you just want to build a good mental world model for robots, honestly, it doesn't have to be human-like. Because robot can have more sensors, better sensors than human eyes. Robots can also have, I guess, better kind of 3D capacity actually compared to human 3D vision. Human 3D visions are good, but not really that good. Like humans struggle with, for example, closing a loop in large 3D space. But you pretty much can kind of train models that can be very good at this kind of task. But I think there's a kind of principle about how 3D vision and world model capacity emerge through development of human intelligence, which is we really have to have some kind of embodied experiences. So we get sense about space, about physics by actually doing things in the world. So I think those kind of learning principle in general could be useful.
Thank you for the answer. On another perspective, like for coding agents you just mentioned, like when they cooperating with each other, is it like easier or harder to model them when collaborating, since you could easily share the context of each other, try to build a common ground?
Yeah, you can do that. I think several things are here, right? So if you have a very well-designed, manually designed multi-agent system, you can actually improve the performance a lot. But obviously you don't want to have a lot of manual design in the future, right? You want agent to assemble a team and really figure out the best way to cooperate with each other automatically without human intervention. So that makes the problem a lot harder. How do they know what the common ground should be to begin with, and how to make sure you can maintain kind of consistent consistency in their decision making, in the sense that you have a long history, right? How do you use this history to make sure you well, you can treat the history as a memory, right? So how do you have a consistent long-term memory so that you don't lose track of what other agents are doing, what you should be all together working towards to, what is the current progress of individual subtasks taken by other agents. So I think that's still pretty much like a fundamental limit of current models.
Thank you.
Thank you. Any other questions?
There's a question in the chat,
Oh,
I think.
Okay, actually, can I see?
the question is, robots using this kind of model would be a very powerful tool to help those who are less physically able. I was wondering if you have encountered any use cases during this development of this kind of model that could be put into practice relatively soon. What are the challenges and could envisioning to encounter? And also, I had some technical issues and I missed the first half of the presentation. Would you be able to get access to the recording? Yeah, we will give you the recording after the talk. And the question.
Right, a real use for people with physical incapacity or disabilities, right? Yes, right now it's happening soon. How to say? Because when you deploy robot to real-world situations, it's a lot harder than you think. I come from Hopkins. Hopkins has a very good nursing school, very good medical school. So I talked to a lot of my colleagues in medical settings, and like say for example ER, OR, and also like say even as simple as physical therapy. So in those cases, they have a lot of challenge that we cannot anticipate as a machine learning researcher. Like say, oftentimes people don't want to be recorded, so you don't actually have videos. You have very sparse signals, like say, for example, in the physical therapy sessions, maybe you can ask them to wear like Fitbit or like some kind of wearable devices to get some kind of signals, or maybe ask for permission for audio recording, right? So you have to find those kind of signals to try to understand what's happening there. A second thing is how to convince them to deploy a robot in their settings that's generally useful and not a burden. That's again like a very big question. So for instance, a lot of the setting we have been exploring is in the ER, in emergency room. If you have been to an ER, I hope you don't need to go there, but if you have been there, it's very inefficient and there's a lot of things happening around. So what are kind of tasks you feel like the current robots can robustly help that can reduce the burden? That's still an open question right now. But I think in generally speaking, if you have a robot that can keep track of every person's movements, infer what they are doing or what they are trying to do, as simple as say, if you look at a bunch of doctors and nurses rushing towards a location, you can kind of understand, maybe there's some emergency happening in that situations. And in those situations, priority system will be useful because you don't want them to stop, look at the robots and spend their precious time to explain the situation to robots. Robot need to automatically understand and try to figure out whether or not you can help. So I think there's a lot of opportunities, but real world deployment is hard, and you need to actually work with a real healthcare provider to figure out the use case.
Thank you very much. Yeah. And any other questions?
So I know in your user study you did a simulated cooking exercise with people.
Yeah.
Is there a reason why you chose that form of interaction over others?
There's no particular reason. I think this cooking is very okay. So we want to kind of have a long horizon task where you have a chance to actually help. It's like a simple task, and oftentimes you don't have a chance to help. So cooking seems like a common task people do a lot around the house. There's a lot of diversity in the thing you want to cook and the way you want to cook. There's a lot of subtasks you can actually help human with, really help human with. So we feel like that's like a pretty common, but also kind of challenging enough kind of task you can start with.
I was wondering this because I think the choice to do that might have implications on your vision. And yes, maybe this is hard to deploy in the real world, but once it becomes real, would you envision this as being like an everyday helper thing, or would it be specialized, as you said, like in physical therapy? Those are two very different contexts.
But they have a different kind of, yes, for sure. In the general hope that the reasoning capacity will be useful. Of course, the ways in which you want to tweak the kind of assistant style or assistant kind of policy, that would be different. I think another kind of I think I haven't talked about that here, but another kind of very exciting direction we're exploring is how you can do test time continuous learning. We actually recently released this tasking benchmark for test and continuous learning agents. So the concept is that once you deploy agents with certain capacity in the real world, they need to continually acquire new knowledge and skills necessary for that kind of environment, right? So I think you can imagine training a robot that have general physical capacity and general kind of social reasoning capacity, but when you deploy that to different situations, you need to continue to adapt and pick up new skills. So I think they need to be specialized and personalized for sure.
That's very interesting. Thank you.
Yeah.
Thank you. And due to the time limit, we can have up to one more question. Any questions? Yeah. If there's no questions, let's thank Tianmin again for his wonderful talk.
All right, thank you.
The event is concluded. Thank you for joining us.
ये वाला गाना भी अच्छा है।